Hello, this is my Unit 11 PowerPoint about chemistry of drugs and medicines. Drugs to its potential effects. The term drug can be explained as a chemical compound that can produce a change in the human body. Some purposes of some drugs include treating a disease, prevention, a diagnosis, and can be used for therapeutic or recreational uses. Drugs can also be called medicines. This term is often used to describe a chemical substance that are given to people for beneficial medical purposes. They are designed to restore or maintain health. For example, antibiotics fighting infections and painkillers are administered to relieve pain. These chemical substances can be harmful or can cause side effects if misused or individual response rejects the drugs. In a social context, there is drugs like alcohol, nicotine and psychoactive that can cause alteration to the moods and behaviour. They can also increase the risk of long-term conditions, and some people can be allergic to certain chemicals which can cause the immune system to overreact. In summary, drugs and medicines are complex interactions within chemistry, biology and human behaviour, meaning that it can change how the body or the mind works. Medicines from the doctor are prescribed to improve or prevent health conditions. All drugs can cause positive or negative effects depending on how they are used and how much dosage. When studying medicine, it is important to understand the key concepts of treatment. There are terms like the placebo, therapeutic window and side effects used for describing how medicines react to the body. A placebo is an inactive treatment used on patients to make them believe that the treatment has worked. It is used in clinical trials to conduct comparisons between placebos and actual effects on the drug. So, for example, using a drug and a sugar pill. Patient symptoms can improve due to the expectations when using the placebo effect method. The placebo effect shows how psychological variables can affect physical health results and emphasise the close relationships between the mind and the body. The term therapeutic window describes the range of doses of a substance that provides successful treatment without causing any dangerous effects. The medication might not have any positive effects if the dosage is less than the lower limit of the window. If it exceeds the upper limit of the therapeutic window, it can cause side effects in the future. Tolerance happens when the body changes and adapts to a certain drug, causing a reduced response over time. This can lead to patients needing a higher dose to achieve successful treatment. Many drugs, such as alcohol, sedatives and painkillers, can cause tolerance. Tolerance raises the risk of dependence and overdose, even though it is a normal biological process. Moving on to side effects. Side effects happens when a treatment causes a problem because it does more than treat the target issue. The impact can range from minor side effects to severe life-threatening side effects. Most medicines produce a therapeutic effect, but in some cases the body can react unintentionally. For example, the effect caused by antihistamines. They block histamine receptors, but these are also located in the brain, so then this can lead to side effects like drowsiness, dry mouth, dizziness and headaches. Another example is chemotherapy. These drugs kill cancer cells by disturbing the growth and division, but also harm the healthy cells, leading to side effects like hair loss, mouth sores, vomiting and changes in appetite. Moving on to structures of drug molecules. The arrangement of atoms within a molecule forms its structural framework. The molecular structure reveals all present atoms together with their bonding connections and the complete molecular form. The construction pattern of a molecule determines its behavioral responses and its ability to interact with other chemicals. The molecular structure of drug compounds in medical treatment determines their ability to bind with bodies, receptors and enzymes. The strength of a drug along with its duration and potential side effects depend on the specific arrangement of the atoms. Scientists use molecular structure knowledge to create drugs that are both safe and effective. Drugs can be found in the same family. The molecular formula can be often very similar. However, small changes in the structure can make a difference in how strong they are, how safe, and the duration they last. So here is some examples. So we've got penicillin antibiotics. This includes a variety of different antibiotics like penicillin G, amoxicillin, methicillin and ampicillin. The structure of the antibiotic includes a B-lactam ring which copies substrate enzymes to help with building cell walls. The bacterial wall construction processes becomes impossible due to ring structure, which results in bacterial death. Each of the antibiotics have different B-lactam rings due to their different chain attachments. For example, amoxicillin has clavulanic acid attached. This means that the antibiotic enhances oral infection as it binds to the enzyme and deactivates it, then breaks it down. Another example is anti-inflammatory drugs. This can include your painkillers such as aspirin, naproxen and ibuprofen. In medicine, these are called NSAIDs. They all have key structural features including carboxylic acids, making them weak acids. They all have a planar aromatic ring structure and high protein binding. So when the body experiences pain and inflammation, this is where the body produces prostaglandins through enzyme activity. When taking these drugs, the S isomer binds to the active site of the CoOX-1 and CoOX-2 enzymes, preventing the production of prostaglandins. The duration of body retention and intensity of effects from these medications depend on the unique structural elements, which include different substituents on the aromatic ring. The stomach tolerance of ibuprofen exceeds naproxen because ibuprofen has a shorter duration of action. And then last example is an opioid painkiller. These are morphine, heroin, codeine and oxycodone. And you've got also fentanyl and hydrocodone. The three-ring structure in these drugs enables them to bind with the receptors in the brain, which results in pain reduction. The strength of these drugs varies because of the tiny structural variations. The addition of a methyl group in codeine results in reduced potency compared to morphine. And then we'll just move on. And then this is just some pictures of each of them, just showing the differences between the two molecular formulas and how they look and what groups they have attached to them, to show how they are different. Moving on to functional group modifications. Scientists perform functional group modifications through small chemical alterations to drug molecules which enhance drug effectiveness and safety and improve delivery to the target areas in the body. Scientists achieve better drug performance through structural modifications of functional groups which exist in drug molecules. The modifications scientists make to drug structures affect their ability to bind with targets and their body movement and duration of action and the potential to trigger adverse reactions. Functional group modification through chemical alteration enables drugs to establish better connections with their biological targets, including enzymes and receptors. The drug target binding strength and specificity depend on the functional group arrangement and the position and chemical structure. The introduction of a hydroxyl and an amine group as a hydrogen bond donors and acceptors leads to enhanced drug target binding through stronger hydrogen bonding formation. Some addition of alkaline and halogen nitro groups to molecules enables better binding for pocket to fit, which results in high drug potency and target specificity. The process enables researchers to create drugs that target specific sites while reducing the side effects. The process of functional group modification enables drugs to reach their intended destinations within the body. The structure of some drugs can prevent them from entering cells and their active compounds from them lasting long enough to find their targets. The polar nature of drugs makes it difficult for them to transverse through cell membranes because of their water-loving properties. Chemists use prodrug formation to temporarily modify specific groups. The body converts prodrugs in their active forms after these medications enter the body. The body converts aspirin into salicylic acid, which functions as the active compound to treat pain and inflammation. Another key reason for modifying functional groups is to make the drug last longer or reduce harmful side effects. So the removal of or the modification of toxic nitro groups leads to significant improvements in drug safety. The additional of the ionizable functional groups like carboxylates or amines enhance drug solubility in water, which makes drug formulation easier. So in summary, scientists achieve better drug performance through precise chemical property and adjustments which enhance drug target interactions, improving drug absorption, stability, solubility and reduce harmful side effects. The process of functional group modification enables scientists to develop chemical compounds into safe and effective medicines which patients can access. Latest new drugs rely on process of molecular structure optimization, which makes it very important for scientists to make sure that the changes are safe and efficient for the new medication. Moving on to organic and inorganic compounds. Chemical compounds that contain identical atomic compositions can exist in multiple structural forms. The scientific term for this phenomenon is isomerism. The specific type of isomerism known as geometric isomerism or cis-trans isomerism occurs in different atomic arrangement to produce distinct molecular shapes. The arrangement of atoms in a double bond or a ring structure leads to geometrical isomerism because it creates different molecular shapes. So cis isomer is when two similar groups are on the same side of the double bond, and trans isomer is the term used when the groups are on opposite sides of the double bond. So just for an example, here they are on the same, and then here they're on opposites. Organic compounds which consist mainly of carbon and hydrogen atoms exhibit isomerism through their double bond structures in alkenes. The fixed positions of atoms attached to a double bond become permanent because this bond restricts free rotation. For example, 2-butene, the methyl groups are opposite sides in trans form, but in cis form, the methyl sides are on the same side, and just shown with the example at the bottom here. Cis isomers show higher polarity, which leads to high boiling points due to the strong forces between the groups. This means that trans and cis form compounds have different boiling points and solubility. In organic compounds, geometrical isomerism can occur in coordination complexes, where the central metal atom is surrounded by other groups called ligands. Inorganic compounds are chemical substances that doesn't contain carbon-hydrogen bonds, which usually includes metals, non-metals, salts, and many more. So for one example is the complex platinum molecule, and this is shown at the bottom, and it consists of ammonia, chloride, and platinum. So in cis form, they are the groups. The chloride atoms are in 90-degree angle in cis form, and in trans form they are opposite, so at 180 angle. These two forms are very important in medicine. So cisplatin is often used for a common cancer treatment due to strong therapeutic effect. The chemotherapy drug binds to the DNA, causing the prevention of cancer cells from dividing. On the other hand, the drug transplatin cannot connect to the DNA to kill the cancer cells from dividing, but it can help the DNA that the cisplatin has already bound to. The arrangement of atoms in space determines drug behaviour in the human body. The spatial arrangement of atoms determines how a molecule will react within the human body. The two isomers contain identical atoms, but their different structures make one useful for medicine and the other useless or dangerous. Geometrical isomerism. The way a drug interacts with its target site in the body depends heavily on the fixed atomic arrangement of double bonds and rings, which makes geometrical isomerism crucial for pharmacological compounds. The different shapes of receptors and enzymes make small changes in drug three-dimensional structure to lead to variations in binding strength and drug effectiveness and side effects. If the wrong isomer is attached, it can cause undesirable biological reactions. Moving on to chiral molecules. Chiral molecules are when there are four different groups are joined to one carbon molecule. The carbon molecule can be called the chiral center. The presence of the carbon atom leads to optical isomerism and the formation of two superimposable mirror images, which get called enantiomers. The two mirror image forms affect plane polarized light by rotating in opposite directions. One example of chiral molecule is lactic acid, which has four different groups attached to it, and it has a carbon chiral with four different groups, which means it can produce two stereoisomers. These can get called L-lactic acid and D-lactic acid. However, on the other hand, if the lack of carbon bonded to four different groups, then it can't produce two stereoisomers, as there are no chiral centres. So some examples are ethanol and methane, and this just shows lactic acid and the four different groups that are attached to it. Moving on to optical isomerism influencing the effects of drugs. So your human bodies are basically chiral because your human body can tell the difference between mirror image forms. So this suggests that we can react to intensity of drugs, side effects and many more. So for example, painkillers have one enantiomer, so it's more effective. This is due to enantiomer fitting well with the receptors in the bodies. Some people's receptors may fit defectively, leading them to have no benefit to the drug at all. Also, some receptors may fit with the wrong enantiomer, causing side effects. Enzymes are chiral. This implies that while one enantiomer may degrade rapidly and exit the body, the other may remain in the body for a long period of time and produce toxic byproducts. Due to these variations, two enantiomers may behave quite differently, even though if they have entered the body at the same dosage. Additional chirality may have an impact on how medicine is processed by the body. Enzymes may degrade one enantiomer more quickly than the other, as they are also chiral. This means that even if the two forms are composed of the same atoms, they may have different safety profiles, intensities, or duration of action. Moving on to drug detection. In drug detection, samples like blood, saliva, urine are taken to identify the drug present in the body. So techniques can be examples like chromatography, microscopy, spectroscopy, screening tests, and mass spectrometry. Chromatography is when samples get separated in different substances. The separation of substances occurs through gas chromatography, which heats substance to create gases that travel through the long heated tube. Then there's also liquid chromatography, which separates delicate or complex drugs used in liquid separation methods. Then moving on to microscopy, in the technical field of using microscopes to view samples and objects that cannot be seen with the unaided eye. Microscopes can analyse the textures of forms of crystals in solid drug samples. When certain medications are combined with reagents, distinctive crystal patterns are formed. This method is used for forensic investigations. And then another method is spectroscopy, which this is a method for drug discovery, as it enables researchers to study molecular dynamics, structural information, and interactional studies. It is employed to access a compound's stability, purity, and composition, as well as to comprehend how it behaves in biological systems. So this is done by shining a light on the sample to see how it reacts. Mass spectroscopy operates a technological which determines the mass to charge ratio of ions. It is an efficient tool for determining the structure and chemical characteristics of different molecules, recognizing unknown compounds and measuring current ones. The ionization technique employed varies depending on the substance nature and the analysis required. The ions start moving at high speeds after ionization, magnetic and electric fields through space based on their mass to charge ratios. And then we've also got immunoassays, are methods detecting biological sample based on specific antigen-antibody reactions. After receiving the sample, the drug will bind to antibody, causing the reaction to reveal a colour change. The positive drug can show the intensity of colour, meaning that the high concentration of the drug is present. Process of finding and testing new drugs. The discovery of new drug molecules requires scientists to use multiple traditional and complementary methods. The discovery of new drug molecules requires scientists to use multiple traditional and contemporary methods. The drug discovery process has advanced through time as scientists now use technologies and methods to identify disease targets and screen large numbers of compounds. The combination of virtual screening with AI-driven design and phenotypic screening and FBDD experimental techniques enable scientists to discover drugs which were previously considered impossible to find. So then there's one way: target identification and validation. This is the discovery of new drug molecules requires scientists to find and confirm biological targets, which usually consist of proteins, enzymes that can cause disease symptoms. The process of target identification requires studying disease molecular mechanism to find specific targets which can be treated through modulation to achieve therapeutic results. Moving on to virtual screening, this depends on computer models which predict how various molecules will bind to disease targets. Scientists employed these models to evaluate thousands of compounds through virtual tests instead of physical compound prediction and testing. So then this is other ways as well. So there's a high throughput screening, which means that they evaluate millions of chemical compounds to detect any binding interactions with the target molecules. The testing process occurs in laboratories which operate machines that perform rapid compound evaluations. Moving on to another way, which is natural screening. The discovery of a new drug compound through natural product screening has been successful in developing cancer treatment, antibiotics, anti-inflammatory medications. Scientists have extracted numerous drugs from plants, fungi, and microorganisms. These organisms create second metabolics for defense purposes. Another method is FBDD, which is fragment-based screening to test individual small chemical fragments instead of completing complex molecules. Another method is CRISPR-based screening method, enables scientists to modify human cell genes for disease research and drug target identification. Another way, which is quite the new way, is AI and machine learning algorithms. They serve as a tool to improve drug discovery processes, starting from target identification until lead optimization. Drug design. The discovery of new medicines have become faster and less expensive through computer technology, which provides precise results in drug design. Computer technology supports all the stages of drug development through its inability to analyze biological targets, stimulate drug behavior, and generate new compound designs. The development of computational tools and AI technology will expand their influence on drug designs to produce better and safer medical treatments for worldwide disease management. And then we have some steps. So these just go through the steps. So step one, process of drug design begins with determining the structural details of biological targets, which typically include proteins that can cause diseases. Scientists use computer tools to study and display three-dimensional protein structures through data obtained from X-ray crystallography and microscopic techniques. This enables the researchers to determine the precise location where the drug molecule can attach to the protein to prevent or modify its function. Step 2 is the molecular docking process. Step 3 involves structure-based screening or ligand-based screening. Step 4, molecular dynamics simulations enable computers to track the evolution of molecular structures and their movements. And step 5, computer programs enable scientists to create brand new drug molecules through their assistance. In conclusion, drug research is a methodological process that starts with comprehending a disease, selecting appropriate biological target, and discovering compounds that safely and successfully alter the activity of the target. Careful testing is necessary at each level to enhance the molecule, ensuring its safety and ensure it functions properly in the body. Investing in these early phases shortens the time it takes to create new drugs, lowers the chance of failure later on, and strengthens our pipeline of possible treatments. With greater help, we can move forward with our ongoing studies faster, investigate new therapeutic concepts, and set up the business to provide patients with modern, cost-effective medicines. And then I've just got my list of references and my references for the background pictures and my bibliography. And yeah, that's it. Thank you for watching.